Hey, welcome to The Night Scientist. I'm so happy you're here with me today. There's something truly magical about taking a moment to pause, to breathe, and to let our minds wander into the vast expanse of the universe that surrounds us. Whether you're settling in for the evening, taking a peaceful break from your day, or simply curious about the incredible story of our planet, I'm delighted you've chosen to spend this time exploring one of the most fascinating tales in all of cosmic history. You know, there's something deeply comforting about understanding our place in the universe. When we look up at the night sky, we're not just seeing distant points of light, we're witnessing an intricate dance that has been unfolding for billions of years, a choreography so precise and beautiful that it speaks to something fundamental about the nature of reality itself. Today, we're going to embark on a journey that will take us back to the very beginning, to a time when our Earth was just forming, when the forces that would shape our entire existence were coming together in ways that still influence every moment of our lives. Today, we're diving into the fascinating world of when the Earth started spinning, the secret language of the universe. This isn't just a story about physics or astronomy, though we'll certainly explore those wonderful subjects. This is a story about the hidden patterns that govern everything around us, the mathematical poetry that writes itself across the cosmos, and the incredible journey that led to this very moment where you and I can share these thoughts together. Imagine, if you will, that you could travel back in time, not just years or centuries, but billions of years, to witness the birth of our solar system. Picture yourself floating in the cosmic darkness, watching as gravity begins its patient work, drawing together the dust and gas that would eventually become our Sun, our Earth, and all the celestial bodies that dance around us today. This is where our story begins, in that primordial soup of cosmic ingredients, where the first stirrings of motion would eventually give birth to the steady rotation that defines our daily experience of life on Earth. Let's start our journey in the most gentle way possible, by imagining ourselves as witnesses to one of the most extraordinary transformations in the history of our universe. Picture, if you can, a time roughly 4.5 billion years ago, when our corner of the galaxy was nothing more than a vast swirling cloud of dust and gas, floating peacefully in the cosmic void. This wasn't the dramatic, explosive beginning you might expect, but rather something more like watching a slow, graceful dance unfold across eons of time. This enormous cloud, which astronomers call a nebula, was primarily composed of hydrogen and helium, the fundamental building blocks that the universe had been creating since the very first moments after the Big Bang. But scattered throughout, this cosmic fog were tiny grains of heavier elements, the remnants of ancient stars that had lived their full lives and scattered their transformed atoms into space. Iron, silicon, carbon, oxygen, all the elements that would one day become part of our planet, part of the oceans, part of the air we breathe, and even part of our own bodies. They were all there, waiting patiently for gravity to begin its slow, inexorable work. Now, here's where the story becomes truly fascinating. Because gravity, despite being the weakest of all the fundamental forces in nature, possesses a quality that makes it absolutely essential to the cosmic story. It never gives up. While electromagnetic forces can repel, while the strong and weak nuclear forces operate only at incredibly small distances, gravity reaches across the vastness of space with infinite patience, always attracting, always pulling, always working to bring matter together. In our peaceful nebula, this meant that even the tiniest fluctuations in density, regions where the gas and dust might be just slightly more concentrated, would begin to attract more material. It's like watching the formation of a whirlpool in slow motion, except this whirlpool was the size of our entire solar system and took millions of years to form. As more and more material was drawn together, something wonderful began to happen. The cloud started to spin. This rotation wasn't random or chaotic. It followed one of the most beautiful principles in all of physics, something called conservation of angular momentum. Think of it this way. Imagine a figure skater performing a spin. When they pull their arms close to their body, they spin faster. When they extend their arms, they slow down. The total amount of rotational motion, what physicists call angular momentum, remains constant, but it can be redistributed. Our nebula was like that figure skater, but in reverse. As it began to collapse under its own gravity, as the vast cloud of gas and dust was pulled inward toward what would eventually become our sun, it had to spin faster and faster to conserve its angular momentum. What started as perhaps an almost imperceptibly slow rotation gradually accelerated over millions of years until the entire cloud was spinning like a cosmic pinwheel. But here's where the magic really begins to unfold. As the cloud spun faster and faster, it began to flatten. Just like pizza dough being spun by a skilled chef, the gravitational collapse and the increasing rotation worked together to transform our roughly spherical cloud into a disk, a beautiful, flat disk of gas and dust with most of the material concentrated at the center, where it was growing denser and hotter as it was compressed by its own gravity. This disk is what astronomers call a protoplanetary disk, and it's one of the most important concepts in understanding how our Earth began its eternal dance of rotation. The material in this disk wasn't static. It was in constant motion, with different regions moving at different speeds, all orbiting around the growing central mass that would become our Sun. The outer regions moved more slowly, like the outer edge of a record player, while the inner regions spun much faster. Within this spinning disk, something truly remarkable was happening. The tiny grains of dust and ice were beginning to stick together. At first, this process was incredibly gentle. Imagine snowflakes slowly accumulating on a winter day, each one adding its small contribution to a growing pile. These cosmic snowflakes were made of rock and ice, and as they drifted through the disk, they occasionally bumped into each other and stuck together through a combination of gravity and static forces. Over thousands and then millions of years, these tiny aggregations grew larger and larger. What started as microscopic dust grains became pebbles, then rocks, then boulders, then small asteroids. This process, called accretion, was the universe's way of building planets from the ground up, literally grain by grain, and throughout this entire process, the growing clumps of matter inherited the rotation of the disk from which they formed. This is crucial to understanding why the Earth spins today. Our planet didn't start spinning because some cosmic force gave it a push, like a top being spun by a child. Instead, it began spinning because it formed from material that was already in motion, material that carried within it the rotational memory of that original nebula. Every particle of dust that came together to create our world brought with it a tiny contribution to what would become Earth's rotation. But the story becomes even more beautiful when we consider that this wasn't a random process. The disk from which our planets formed had a preferred direction of rotation, inherited from the original angular momentum of the nebula. This is why all the planets in our solar system orbit the Sun in the same direction, and why most of them also rotate on their axes in that same direction. It's as if the entire solar system remembers that ancient cosmic dance, that slow pirouette of the nebula from which we all emerged. As our proto-Earth continued to grow, accumulating more and more material from the swirling disk around the young Sun, its rotation became more and more pronounced. But this wasn't a smooth, gentle process. The early solar system was a much more chaotic place than it is today, filled with countless small bodies, asteroids, comets, and planetesimals, all following their own complex orbits and occasionally colliding with the growing planets. Each collision added not only mass to the growing Earth, but also angular momentum. Some impacts would speed up the rotation, others might slow it down or change its axis slightly. The final rotation of our planet was the result of countless such interactions, a kind of cosmic averaging process that took millions of years to settle into the steady, reliable spin that we experience today. And here's something truly wonderful to consider. That ancient dance, that original rotation imparted to our world billions of years ago, is still with us today. Every sunrise you witness, every sunset that paints the sky in brilliant colours, every star that wheels overhead during the night, all of these daily miracles are direct consequences of that primordial spin, that cosmic inheritance from the very formation of our solar system. There's something deeply poetic about the way mathematics describes the motion of our world. If we listen carefully to the language of physics, we can hear the universe speaking to us in equations and principles that reveal the hidden order underlying all the beauty and chaos we see around us. The rotation of our Earth isn't just a random occurrence. It's governed by mathematical laws so fundamental and universal that they apply equally to spinning galaxies, dancing atoms, and everything in between. Let's explore this secret language together, starting with one of the most beautiful concepts in all of physics, angular momentum. If you've ever watched a ballerina pirouette or observed the way water spirals down a drain, you've witnessed this principle in action. Angular momentum is the rotational equivalent of regular momentum. Just as a moving object tends to keep moving in a straight line unless acted upon by a force, a spinning object tends to keep spinning unless something interferes with its rotation. The mathematical expression of angular momentum is elegantly simple. L equals I times omega. Where L represents angular momentum, I represents the moment of inertia, which describes how mass is distributed around the axis of rotation, and omega represents the angular velocity, how fast something is spinning. But don't let the simplicity of this equation fool you. It describes one of the most profound and persistent forces in our universe. When we apply this principle to our Earth, we discover something remarkable. Our planet, with its mass of approximately 6 trillion kilograms distributed in a roughly spherical shape, possesses an enormous amount of angular momentum. Once spinning, it wants to keep spinning, and it takes a tremendous force to change that rotation significantly. This is why our days have remained roughly the same length for billions of years, why we can rely on the sun to rise in the east and set in the west, why the stars follow their predictable paths across our night sky. But the mathematics goes deeper than this. The conservation of angular momentum explains not just why the Earth continues to spin, but also helps us understand how that spin originated in the first place. Remember our cosmic nebula, slowly collapsing under its own gravity? As it shrank, its rotation had to increase to conserve angular momentum, just like that figure skater pulling in her arms. The mathematics demanded it. There was no choice in the matter. This brings us to another beautiful mathematical concept, Kepler's laws of planetary motion. Johannes Kepler, working in the early 1600s with observations made by Tycho Brahe, discovered that planets follow elliptical orbits around the Sun and that there are precise mathematical relationships governing their motion. His second law is particularly relevant to our story. A line drawn from a planet to the Sun sweeps out equal areas in equal times. What this means is that when a planet is closer to the Sun in its elliptical orbit, it moves faster, and when it's farther away, it moves more slowly. This is another manifestation of conservation of angular momentum, and it applies not just to orbital motion, but to rotational motion as well. As our proto-Earth formed from the collapsing disk of material around the young Sun, the same mathematical principles that govern planetary orbits were also shaping its rotation. The gravitational force itself follows a beautifully simple mathematical law, discovered by Isaac Newton and later refined by Albert Einstein. The force of gravity between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. This inverse square law creates the precise conditions necessary for stable orbits and predictable rotation patterns throughout the universe. But perhaps the most profound mathematical insight comes from Einstein's theory of relativity, which revealed that space and time are not separate entities, but part of a unified fabric called space-time. When massive objects like planets spin, They actually drag space-time along with them in a phenomenon called frame dragging, or the lens-thirring effect. This means that Earth's rotation creates a subtle twist in the very geometry of space around our planet. The universe itself bears the mathematical signature of our world's ancient spin. The mathematics of Earth's rotation also reveals itself in the complex patterns of precession. Just like a spinning top that wobbles as it slows down, Earth's rotational axis traces out a slow circle in space over a period of approximately 26,000 years. This precession is caused by the gravitational influences of the Moon and Sun acting on Earth's equatorial bulge, a slight flattening at the poles caused by our planet's rotation. This precession follows precise mathematical laws that allow us to predict exactly where Earth's axis will be pointing thousands of years into the future or past. Right now, our North Pole points roughly toward the star we call Polaris, but in about 12,000 years, it will point toward the bright star Vega instead. The mathematics tells us exactly when this transition will occur and how it will unfold. Even more remarkably, the mathematics of rotation reveals itself in the very shape of our planet. Earth is not a perfect sphere, but an oblate spheroid, flattened at the poles and bulging at the equator due to the centrifugal force created by its rotation. The amount of this flattening can be calculated precisely using the principles of fluid dynamics and the mathematics of rotating bodies. The difference between Earth's equatorial and polar diameters is about 43 kilometers, a testament to the power of rotational forces acting over billions of years. The Coriolis effect, which influences weather patterns, ocean currents, and even the direction that water drains from a bathtub, is another beautiful manifestation of the mathematics of rotation. This apparent force arises because different parts of our spinning Earth are moving at different velocities. The equator, being farther from the axis of rotation, moves faster than regions closer to the poles. This creates apparent deflections in the paths of moving objects, deflections that follow precise mathematical formulas and create the spiraling patterns we see in hurricanes and the great ocean currents that help regulate our planet's climate. Perhaps most beautifully of all, the mathematics of Earth's rotation connects us to the fundamental constants of nature. The period of our planet's rotation, approximately 24 hours, is intimately connected to the gravitational constant, the mass of the Earth, the distance to the Moon, and countless other physical parameters that define our cosmic environment. Change any one of these values significantly, and the length of our day would be dramatically different. This mathematical interconnectedness extends throughout the universe. The same equations that describe Earth's rotation also govern the spin of distant galaxies, the orbital dance of binary star systems, and the quantum mechanical spin of subatomic particles. From the largest structures in the cosmos to the smallest constituents of matter, the universe speaks the same mathematical language of rotation and angular momentum. The mathematics also reveals something profound about time itself. Our measurement of time, the second, the minute, the hour, the day, is fundamentally based on Earth's rotation. Before atomic clocks, time was literally defined by the rotation of our planet. Even today, our calendar systems and our biological rhythms are synchronized with this ancient cosmic dance. The mathematics of rotation has become so deeply embedded in human culture and physiology that we can't separate our experience of time from the spinning motion that began when our world first formed. Sometimes the most beautiful stories in the universe are also the most dramatic, and the story of how Earth acquired its current rotation includes one of the most spectacular events in the history of our solar system. This event was so significant that it not only affected how fast our planet spins, but also gave us one of the most beautiful sights in our night sky, our moon. To understand this cosmic drama, we need to travel back in time once again to an era about 4.5 billion years ago, when our solar system was still a young and chaotic place. The planets had largely formed through the process of accretion we discussed earlier, but the solar system was still filled with countless smaller bodies, asteroids, comets, and planetesimals that hadn't yet found their final homes. Collisions were common, and some of these impacts were truly titanic in scale. Our early Earth was quite different from the world we know today. It was probably spinning much faster, with days lasting perhaps only 6 to 8 hours instead of our current 24. The surface was still mostly molten from the heat of formation and constant bombardment by space debris. There was no oxygen in the atmosphere, no oceans as we know them, and certainly no life of any kind. It was a world in the process of becoming, still writing the early chapters of its geological story. Into this scenario comes one of the most important characters in Earth's story, a Mars-sized planetary body that scientists have named Theia, after the Greek Titaness, who was the mother of the moon goddess Selene. Theia was following its own orbit around the young sun, an orbit that would eventually bring it into a catastrophic encounter with our forming Earth.
The collision between Earth and Theia was not a head-on impact, which would have been utterly devastating and might have shattered both bodies completely. Instead, it was what scientists call a glancing blow. Theia struck Earth at an angle, delivering a tremendous amount of energy and angular momentum to our planet, while also blasting enormous amounts of material into space. Try to imagine the scale of this event. Theia was roughly the size of Mars, with a mass about 10% of Earth's mass. When it collided with our planet, the impact released energy equivalent to billions of the most powerful nuclear weapons ever created, all detonating simultaneously. The collision was so violent that it completely melted both bodies, creating a temporary structure that scientists sometimes call the synestia, a donut-shaped cloud of vaporized rock spinning rapidly in space. This collision had profound effects on Earth's rotation. The angular momentum carried by Theia was added to Earth's existing spin, but because the impact was at an angle rather than head-on, it didn't simply speed up our planet's rotation in the same direction it was already spinning. Instead, it changed both the rate of rotation and the tilt of Earth's rotational axis. Before the collision, Earth's rotational axis was probably nearly perpendicular to the plane of its orbit around the Sun, but the impact with Theia knocked our planet askew, giving it the axial tilt of about 23.5 degrees that we have today. This tilt might seem like a minor detail, but it's actually one of the most important factors in making Earth habitable. This axial tilt is what gives us our seasons. As Earth orbits the Sun, first the northern hemisphere and then the southern hemisphere is tilted toward our star, creating the annual cycle of spring, summer, autumn, and winter that has shaped the evolution of life on our planet. The debris blasted into space by the collision didn't simply drift away into the cosmos. Much of it remained in orbit around Earth, held by our planet's gravity. Over a period of perhaps a few hundred years, an incredibly short time in geological terms, this debris began to clump together through the same process of accretion that had originally formed the planets. The result was our moon, born from the violence of cosmic collision, but destined to become one of the most stabilizing influences on Earth's rotation and climate. The formation of the moon had immediate and long-lasting effects on Earth's rotation. In the early days after the collision, when the moon was much closer to Earth than it is today, the gravitational interaction between our planet and its new satellite was much stronger. The moon's gravity raised enormous tides on the still molten Earth, and these tides acted as a brake on our planet's rotation, gradually slowing it down from those early 6-hour days to the 24-hour cycle we know today. This tidal braking continues even now, though much more slowly. The moon is gradually moving away from Earth, currently at a rate of about 3.8 centimeters per year, and as it does so, it continues to slow down our planet's rotation. Our days are getting longer. by about 1.7 milliseconds per century. It's an almost imperceptibly slow change, but over geological timescales, it adds up to significant differences. The Moon's influence on Earth's rotation goes beyond just slowing it down. Our satellite also acts as a stabilizer for Earth's axial tilt. Without the Moon, gravitational perturbations from the other planets would cause Earth's rotational axis to wobble chaotically over periods of millions of years. Mars, which lacks a large stabilizing satellite, experiences exactly this kind of chaotic variation in its axial tilt, swinging from nearly upright to tilted more than 60 degrees from vertical dot. The stabilization of Earth's rotation has been crucial for the development and maintenance of life on our planet. The consistent seasonal patterns created by our stable axial tilt have allowed complex climate systems to develop and persist over geological time. The regular day-night cycle has influenced the evolution of biological rhythms that are still embedded in the genetic code of virtually every living organism on Earth. The story of the Great Collision also helps us understand something profound about the nature of cosmic evolution. The same violent event that could have destroyed our planet entirely instead gave us some of our most important and beautiful features: our moon, our seasons, our stable climate, and ultimately the conditions that allowed life to flourish. It's a reminder that in the universe, destruction and creation are often intimately connected, two sides of the same cosmic coin. Modern computer simulations of the collision between Earth and Theia reveal just how precisely balanced this event had to be to produce the world we know today. If Theia had been significantly larger or smaller, if the angle of impact had been different, if the collision had occurred earlier or later in Earth's formation, the outcome could have been completely different. We might have ended up with no moon at all, or with multiple smaller moons, or with a planet spinning so fast or so slow that life as we know it could never have developed. The mathematical modeling of this ancient collision represents one of the most sophisticated applications of computational physics to planetary science. Scientists use supercomputers to simulate the complex interactions of gravity, thermodynamics, and fluid dynamics that occurred during those few hours when Earth and Theia merged and separated. These simulations help us understand not only what happened to our own planet, but also how similar processes might unfold around other stars, potentially creating other worlds where life might arise. The Great Collision between Earth and Theia reminds us that our planet's rotation, something so fundamental to our daily experience that we rarely think about it, is the result of cosmic events of almost unimaginable violence and beauty. Every sunrise and sunset, every change of season, every tide that rises and falls, carries within it the memory of that ancient impact, that moment when two worlds became one and gave birth to the moon that lights our nights and stabilizes our days. If we could somehow step outside of our solar system and observe it from a distance, floating peacefully in the cold darkness of interstellar space, we would witness one of the most elegant and beautiful dances in the entire universe. Every planet, every moon, every asteroid and comet moves in precise harmony with every other object, all choreographed by the invisible hand of gravity. And at the center of this cosmic ballet, our Earth spins steadily on its axis, its rotation, intimately connected to the gravitational symphony playing out around it. Gravity is perhaps the most mysterious of all the fundamental forces. Unlike the electromagnetic force, which can both attract and repel, gravity only attracts. Unlike the strong and weak nuclear forces, which operate only at incredibly tiny distances, Gravity reaches across the vast emptiness of space to influence objects billions of kilometers apart. And unlike the other forces which can be shielded or blocked, gravity is always present, always pulling, always shaping the architecture of the cosmos. Albert Einstein showed us that gravity isn't really a force in the traditional sense, but rather a curvature in the fabric of spacetime itself. Massive objects like stars and planets create dimples and valleys in this fabric, and other objects naturally follow the curved paths created by these distortions. It's a beautiful and elegant description that transforms our understanding of planetary motion from a mechanical process of forces and accelerations into something more like a cosmic dance where partners naturally follow the curves and contours of the universal dance floor. In our solar system, the sun's enormous mass creates the dominant gravitational field that keeps all the planets in their orbits. But each planet also creates its own gravitational field, influencing not only its moons and ring systems, but also subtly affecting the orbits and rotations of other planets. Jupiter, with its massive bulk, acts as a kind of gravitational conductor, orchestrating the movements of countless smaller bodies and even influencing the long-term stability of Earth's orbit. The relationship between Earth's rotation and the gravitational dance of our solar system is beautifully complex. As our planet spins on its axis, it experiences what's called tidal forces from both the Sun and the Moon. These forces arise because gravity is stronger on the parts of Earth that are closer to these massive bodies and weaker on the parts that are farther away. The difference in gravitational pull across Earth's diameter creates a stretching effect that slightly deforms our planet's shape. The Moon's gravitational influence is particularly important because while it's much smaller than the Sun, it's also much closer to Earth. This proximity means that lunar tidal forces are actually stronger than solar tidal forces, making the Moon the primary driver of our ocean tides. But the Moon doesn't just move our oceans, it also influences Earth's rotation itself through a process called tidal friction. As Earth rotates beneath the tidal bulges raised by the Moon's gravity, friction between the moving water and the ocean floor, as well as within the solid Earth itself, gradually converts some of Earth's rotational energy into heat. This process is slowly but steadily slowing down our planet's rotation, making our days slightly longer with each passing century. It's a remarkably gentle process. The change is so small that it's barely measurable over human lifetimes, but over geological timescales, it adds up to significant changes. The gravitational dance extends far beyond just Earth and Moon. The regular pattern of day and night on Earth is influenced by our planet's position relative to the Sun. But this relationship is constantly modified by the gravitational effects of other planets. The slight variations in Earth's orbital distance from the Sun, combined with changes in our planet's axial tilt caused by gravitational perturbations from other planets, create cycles that influence Earth's climate over periods of tens of thousands of years. These cycles, known as Milankovitch cycles after the Serbian astronomer who first described them mathematically, demonstrate how intimately connected Earth's rotation and orbital motion are to the larger gravitational environment of our solar system. The gradual changes in the shape of Earth's orbit, the slow precession of our rotational axis, and periodic variations in the tilt of that axis all combine to create complex patterns of climate change that have influenced the evolution of life. On our planet, Jupiter plays a particularly fascinating role in this gravitational symphony. Its enormous mass, more than twice the mass of all other planets combined, makes it the dominant gravitational influence in the outer solar system. Jupiter's gravity helps to protect Earth from catastrophic asteroid and comet impacts by either capturing these potentially dangerous objects or deflecting them away from the inner solar system. In this sense, Jupiter acts as a kind of gravitational shield, helping to maintain the stable conditions that allow life to flourish on Earth. But Jupiter's influence goes even deeper. The gravitational interaction between Jupiter and the other planets creates subtle resonances, mathematical relationships between orbital periods that help to stabilize the entire solar system. These resonances prevent the planets from drifting into chaotic, unstable orbits that could dramatically alter Earth's rotation and climate. The precise mathematical relationships between planetary orbits act like cosmic clockwork, keeping everything running smoothly for billions of years. That the concept of gravitational resonance, beautifully illustrated by the relationship between Jupiter and Saturn. These two giant planets complete their orbits in a nearly exact 2:5 ratio. For every 2 orbits that Jupiter completes around the Sun, Saturn completes almost exactly 5. This relationship isn't coincidental. It's the result of gravitational interactions that have gradually adjusted the planet's orbits over millions of years to achieve this stable configuration. Similar resonances exist throughout the solar system, creating a web of gravitational relationships that connects every orbiting body to every other. The moons of Jupiter display beautiful resonance patterns among themselves, as do the rings of Saturn and the asteroid belt between Mars and Jupiter. These patterns demonstrate that gravity isn't just a simple attractive force, but a complex organizing principle that creates order and stability on cosmic scales. The dance of gravity also reveals itself in the phenomenon of precession that we mentioned earlier. Earth's rotational axis slowly traces out a circle in space over a period of about 26,000 years, like a spinning top wobbling as it slows down. This precession is caused primarily by the gravitational influence of the Moon and Sun acting on Earth's equatorial bulge, the slight flattening at our planet's equator, caused by its rotation. But the precession of Earth's axis is also influenced by the gravitational fields of all the other planets. Venus, Mars, Jupiter, Saturn, each contributes its small but measurable influence to the complex motion of Earth's rotational axis. Modern astronomers can predict the exact position of Earth's axis thousands of years into the future or past. By taking into account all these gravitational influences and solving the complex equations that describe their interactions, perhaps most remarkably, the gravitational dance of our solar system has remained stable for over 4 billion years, maintaining the conditions necessary for liquid water to exist on Earth's surface and for life to evolve and flourish. This long-term stability is not guaranteed. Computer simulations show that solar systems can easily become chaotic, with planets either colliding with each other or being ejected into interstellar space. The fact that our solar system has remained stable for so long suggests that the initial conditions of its formation were precisely tuned to create this beautiful, enduring gravitational harmony that, as we continue to discover planets around other stars, we're learning that stable planetary systems like ours may be relatively rare. Many exoplanetary systems show signs of past instability, with planets in highly elliptical orbits or in configurations that suggest dramatic migrations from their original positions. This makes us appreciate even more the delicate gravitational balance that has preserved Earth's rotation and orbit for billions of years, creating the stable foundation upon which the entire story of life on our planet has unfolded. There's something deeply comforting about the rhythm of days and nights, The steady alternation of light and darkness that has marked the passage of time since Earth first began to spin. This rhythm is so fundamental to our experience of life that we rarely pause to consider what an extraordinary thing it represents. A perfect synchronization between our planet's rotation and our star's radiance that has created the temporal framework within which all of terrestrial life has evolved. The length of Earth's day, 24 hours, feels natural and inevitable to us, but it's actually the result of a complex interplay of forces that has been millions of years in the making. When Earth first formed, as we've learned, it was spinning much faster, with days lasting perhaps only 6 to 8 hours. The gradual slowing of our planet's rotation to its current rate has been one of the most important factors in creating the stable, life-friendly environment we know today. This slowing has been caused primarily by tidal friction. The same force that creates our ocean tides also acts as a gentle but persistent brake on Earth's rotation. As our planet spins beneath the tidal bulges raised by the moon's gravity, the friction between moving water and the ocean floor and within the solid Earth itself gradually converts rotational energy into heat. It's a process so slow that we can barely measure it over human lifetimes, but over geological timescales, it has transformed the rhythm of our world. The beauty of this process lies in its gentleness and consistency. Unlike the dramatic collisions and catastrophic events that shaped the early solar system, tidal friction operates with the patience of geological time, making tiny adjustments that accumulate into major changes over millions of years. It's the universe's way of fine-tuning the conditions on our planet, gradually creating the stable 24-hour cycle that has become the foundation of biological timekeeping on Earth. Our current day length represents a kind of sweet spot for life as we know it. Days that are too short don't allow enough time for complex biological processes to unfold, while days that are too long create extreme temperature variations between the heated day side and the cold night side of the planet. The 24-hour cycle provides just the right balance, allowing the surface to warm during the day and cool during the night without reaching extremes that would be hostile to life. This rhythm has become deeply embedded in the biology of virtually every living organism on Earth, from the smallest bacteria to the largest mammals. Internal biological clocks known as circadian rhythms synchronize cellular processes with the daily cycle of light and darkness. These rhythms are so fundamental that they persist even when organisms are isolated from external time cues, suggesting that the 24-hour day has literally shaped the evolution of life at the molecular level. The alternation of day and night also drives some of the most important processes in Earth's climate system. During the day, solar energy heats the surface, driving evaporation from oceans and lakes, fueling photosynthesis in plants, and creating temperature differences that generate winds and weather patterns. At night, the surface cools through radiation to space, allowing water vapor to condense into dew and clouds, and creating different patterns of air movement that help to distribute heat around the planet. This daily breathing of Earth's atmosphere, the expansion during the day and contraction at night, creates atmospheric tides that are much subtler than ocean tides, but equally important for understanding how our planet works as an integrated system. These atmospheric tides influence wind patterns, precipitation cycles, and even the distribution of gases in the atmosphere. They're part of the complex web of interactions that connect Earth's rotation to every aspect of our planet's climate and weather. The position of the sun in the sky during each day follows patterns that are both mathematically precise and beautifully predictable. The path of the sun across the heavens, higher in summer, lower in winter, is determined by Earth's axial tilt and its orbital position around the sun. This creates the seasonal cycle that has been one of the most important factors in shaping the evolution of life on Earth. Ancient civilizations recognized the importance of these solar patterns and built some of humanity's most impressive monuments to mark and celebrate them. Stonehenge in England, the pyramids of Egypt, the temples of Angkor Wat in Cambodia. All of these structures contain precise astronomical alignments that demonstrate our ancestors' deep understanding of Earth's rotational and orbital cycles. They knew that understanding the rhythm of days and nights and the longer cycles of seasons and years was essential for agriculture, navigation, and timekeeping. The invention of mechanical clocks in medieval Europe represented a revolutionary attempt to capture and regularize the natural rhythm of Earth's rotation. Before clocks, time was measured by the position of the sun, the length of shadows, and the changing patterns of stars in the night sky. All of these natural timepieces were directly connected to Earth's rotation, making the spinning of our planet the fundamental standard for human timekeeping. Even today, despite the incredible precision of atomic clocks, the definition of a day is still fundamentally based on Earth's rotation. The second, the basic unit of time in our modern system, was originally defined as 1/86,400th of a mean solar day. Although atomic clocks are now more precise than Earth's rotation, we still occasionally add leap seconds to our timekeeping systems to keep our clocks synchronized with our planet's spin. The relationship between Earth's rotation and human culture goes far deeper than just timekeeping. The rhythm of day and night has influenced art, literature, religion, and philosophy throughout human history. The symbolism of sunrise as rebirth and renewal, of sunset as ending and reflection, of noon as clarity and midnight as mystery. These associations are so deeply embedded in human consciousness that they appear in virtually every culture on Earth. Modern life has somewhat disconnected us from the natural rhythm of days and nights. Electric lighting allows us to extend our activities far into the night, while global communications and travel create situations where we're active during what would naturally be our sleeping hours. But research in chronobiology, the study of biological time, shows that our bodies still maintain strong connections to the ancient rhythm of Earth's rotation. Disruptions to this rhythm, such as those experienced by shift workers or frequent travelers crossing time zones, can have significant effects on health and well-being. The rhythm of days and nights also plays a crucial role in Earth's energy balance. During the day, our planet absorbs energy from the sun, warming the surface, the atmosphere, and the oceans. At night, this energy is radiated back to space, cooling the planet. The balance between incoming solar energy and outgoing thermal radiation determines Earth's average temperature and drives all of the climate and weather patterns that make our planet habitable. This daily energy cycle is modified by Earth's rotation in important ways. The spinning of our planet ensures that no part of the surface is heated continuously. Everywhere experiences both day and night, preventing the extreme temperature differences that would develop if one side of Earth always faced the sun. The atmosphere and oceans help to smooth out these temperature variations, but the fundamental pattern is set by the steady rotation that brings each part of the planet alternately into sunlight and shadow dot as we look to the future. The rhythm of days and nights will continue to evolve, though very slowly. Earth's rotation will continue to slow due to tidal friction, making each day slightly longer than the last. In the far future, many billions of years from now, Earth and the Moon may become tidally locked, with the same side of Earth always facing the Moon, just as the same side of the Moon always faces Earth today. But these changes will unfold over timescales so vast that they're almost impossible to comprehend from our human perspective. For now, we can take comfort in the steady, reliable rhythm that has marked the passage of time on Earth for billions of years. Each sunrise and sunset, each cycle of day and night, connects us to the fundamental rotation of our planet and to the cosmic forces that set our world spinning in the first place. In the simple alternation of light and darkness, we can read the story of Earth's formation, the influence of the Moon, the power of gravity, and the mathematical precision that governs the motion of our solar system. It's a rhythm that has shaped the evolution of life itself and continues to mark the passage of our days with quiet, persistent beauty. Beneath the surface of our everyday experience lies a hidden world of forces and fields that shape every aspect of Earth's rotation and our planet's interaction with the cosmos. These invisible influences are just as real and important as the visible phenomena we can observe directly, but they require the careful eye of science to reveal their presence and understand their profound effects on our spinning world. Perhaps the most mysterious of these invisible forces is Earth's magnetic field, a vast dynamic shield that surrounds our planet and extends far into space. This magnetic field is generated deep within Earth's core by the motion of molten iron and other metals in a process that scientists call the geodynamo. The connection between Earth's rotation and its magnetic field is intimate and complex. Our planet's spin helps drive the convective currents in the liquid outer core that generate the magnetic field, while the magnetic field itself influences the rotation through subtle electromagnetic effects. The geodynamo is one of the most beautiful examples of how different physical processes can work together to create something greater than the sum of their parts. Heat from radioactive decay in Earth's core creates convection currents in the molten metal, much like the way hot air rises from a heated surface. But because Earth is rotating, these convection currents don't simply rise straight up. They're twisted and turned by the Coriolis effect, creating complex spiral patterns that generate electric currents, which in turn create magnetic fields. This process requires a delicate balance of conditions. The core must be hot enough to keep the iron molten. The planet must be rotating fast enough to create the necessary Coriolis effects, and the convection must be vigorous enough to generate sufficient electric currents. If any of these conditions were significantly different, Earth might not have a magnetic field at all, a situation that would have profound consequences for life on our planet. Earth's magnetic field serves as a shield that protects us from the constant stream of charged particles flowing from the sun, known as the solar wind. Without this protection, these high-energy particles would gradually strip away our atmosphere, as appears to have happened to Mars, which has only a very weak magnetic field. The interaction between the solar wind and Earth's magnetic field creates the magnetosphere, a vast region around our planet where charged particles are trapped and deflected. The northern and southern lights, aurora borealis and aurora australis, are visible manifestations of this invisible interaction. When charged particles from the solar wind manage to penetrate Earth's magnetic field near the poles, they collide with atoms in our atmosphere, causing them to emit light in the beautiful, dancing curtains of color that have fascinated humans throughout history. These auroras are like cosmic lighthouses, marking the places where the invisible forces surrounding our planet become visible to our eyes. But Earth's magnetic field is not constant. It varies in strength and direction over timescales ranging from seconds to millions of years. The most dramatic changes are magnetic reversals, when the north and south magnetic poles flip positions. These reversals have occurred hundreds of times throughout Earth's history, with the most recent one happening about 780,000 years ago. During a reversal, which can take thousands of years to complete, Earth's magnetic field weakens significantly. Before re-establishing itself with opposite polarity, the timing of these magnetic reversals appears to be related to changes in the dynamics of Earth's core, which are in turn influenced by our planet's rotation. As Earth's rotation has slowed over geological time due to tidal friction, the conditions in the core have changed, affecting the geodynamo and potentially influencing the frequency of magnetic reversals. It's another example of how Earth's rotation connects to processes throughout our planet, from the surface all the way down to the center dot. Another invisible force that shapes Earth's rotation is the solar wind itself, that constant stream of charged particles flowing from the sun at speeds of hundreds of kilometers per second. While the solar wind is primarily deflected by Earth's magnetic field, it still exerts a subtle pressure on our planet and its magnetosphere. This pressure varies with the sun's activity cycle, creating small but measurable effects on Earth's rotation and the length of our days. The sun's activity follows an 11-year cycle of increasing and decreasing intensity, marked by changes in the number of sunspots, solar flares, and coronal mass ejections. During periods of high solar activity, the increased solar wind pressure can slightly affect Earth's rotation, while the enhanced magnetic field interactions can influence the upper atmosphere in ways that create subtle changes in the planet's moment of inertia, its resistance to rotational changes. Even more subtle are the effects of electromagnetic radiation from distant astronomical objects. Pulsars, rapidly rotating neutron stars that emit beams of radio waves, create regular pulses of electromagnetic energy that sweep across Earth like cosmic lighthouses. While these pulses are incredibly faint by the time they reach us, they're so regular that they can be used as cosmic clocks, allowing astronomers to detect tiny variations in Earth's rotation that would be impossible to measure any other way. Study of pulsar timing has revealed that Earth's rotation is influenced by a surprising variety of factors, from changes in atmospheric pressure to seasonal variations in the distribution of water and ice on our planet's surface. Even major earthquakes can slightly alter Earth's rotation by redistributing mass within the planet. The 2011 earthquake and tsunami in Japan, for example, shifted enough mass to speed up Earth's rotation by about 1.8 microseconds, a change so small that it's utterly imperceptible in daily life, but measurable with modern instruments. The invisible influence of quantum mechanics also plays a role in Earth's rotation, though in ways that are still not fully understood. At the atomic level, the electrons, protons, and neutrons that make up Earth's matter all have a property called spin, a quantum mechanical angular momentum that contributes to the overall rotation of our planet. While the contribution of individual particles is unimaginably small, the collective effect of all the atoms in Earth may have subtle influences on our planet's rotation that scientists are only beginning to explore. Dark matter, the mysterious substance that makes up about 85% of all matter in the universe, may also have invisible effects on Earth's rotation. As our solar system moves through the galaxy, we pass through regions with different densities of dark matter. Some theoretical models suggest that these variations could create tiny, but detectable changes in Earth's rotation through gravitational effects. While such influences have not yet been confirmed, the search for them represents one of the frontiers of modern physics and astronomy. Relationship between Earth's rotation and the expansion of the universe itself is another area where invisible forces may be at work. As space itself expands, carried along by the mysterious dark energy that appears to be accelerating the universe's expansion, there may be subtle effects on the rotation of objects within that expanding space. These effects would be incredibly small, far too small to measure with current technology, but they represent a connection between Earth's daily spin and the ultimate fate of the cosmos. Perhaps most remarkably, Earth's rotation is connected to the fundamental constants of physics themselves. The strength of gravity, the speed of light, the mass of elementary particles, all of these constants help determine the conditions under which planets can form and maintain stable rotations. If any of these constants were significantly different, the universe might be a place where stable, rotating planets like Earth could not exist at all. The invisible forces that shape Earth's rotation remind us that our planet is not an isolated object spinning in empty space, but rather an integral part of a vast interconnected cosmos. From the quantum fluctuations in the vacuum of space to the large-scale structure of the universe, from the magnetic fields generated in our planet's core to the solar wind streaming from our star, countless invisible influences contribute to the steady rotation that marks our days and shapes our lives. Understanding these invisible forces requires some of humanity's most sophisticated scientific instruments and theoretical frameworks. Satellites monitor Earth's magnetic field from space. Deep underground laboratories study the properties of fundamental particles, and radio telescopes listen to the cosmic lighthouses of distant pulsars. Each new discovery reveals more connections between Earth's rotation and the broader universe, painting a picture of a cosmos where everything is connected to everything else through the invisible threads of physical law. As we continue to explore these connections, we gain not only a deeper understanding of how our planet works, but also a greater appreciation for the delicate balance of forces that makes Earth's stable rotation and life itself possible. The invisible forces that surround us are not abstract concepts from physics textbooks, but active participants in the cosmic dance that has shaped our world and continues to influence every moment of our existence on this spinning planet we call home. There's something almost mystical about time, the way it flows around us, through us, carrying us forward from moment to moment while remaining itself mysterious and elusive. We measure time, divide it, save it, spend it, and sometimes feel as though we're racing against it. But rarely do we pause to consider that our entire human understanding of time is fundamentally connected to the ancient rotation of our planet. The architecture of time itself, the seconds, minutes, hours, days, months, and years that structure our lives, is built upon the cosmic foundation of Earth's spin and orbital dance around the sun. Long before the invention of clocks, our ancestors understood that time was not an abstract concept, but something intimately connected to the celestial movements they observed in the sky. The rising and setting of the sun marked the most basic unit of time, the day. The changing phases of the moon provided a longer rhythm, the month. The cycle of seasons, driven by Earth's tilted axis as it orbited the sun, gave structure to the year. All of these natural timepieces were directly connected to the motions of our planet and its satellite, making Earth's rotation and orbital motion the fundamental clockwork of human civilization. The day our most basic unit of time, is defined by the rotation of Earth on its axis. But even this apparently simple definition conceals layers of complexity that reveal the deep connections between timekeeping and astronomy. There are actually several different ways to define a day, each based on different celestial reference points, and each telling us something different about how Earth moves through space. A solar day, the time from one noon to the next, when the sun reaches its highest point in the sky, is about 4 minutes longer than a sidereal day, which is the time it takes Earth to complete one full rotation relative to the distant stars. This difference exists because Earth is not only rotating on its axis, but also orbiting around the sun. During the course of one rotation, Earth has moved slightly along its orbital path, so it must rotate a little bit more to bring the sun back to the same position in the sky. This 4-minute difference might seem trivial, but it reveals something profound about the relationship between Earth's rotation and its orbital motion. The two movements are not independent, they're part of a single, integrated dance that connects the rhythm of our days to the larger rhythm of our year. Ancient astronomers understood this connection intuitively, using careful observations of the sun and stars to develop calendars that could predict the seasons and guide agricultural activities. The measurement of time has always been one of humanity's greatest scientific and technological challenges. The earliest clocks were essentially mechanical models of astronomical motions, sundials that tracked the sun's apparent movement across the sky, water clocks that used the steady flow of water to measure intervals, and eventually mechanical clocks with gears and springs that attempted to reproduce the regular rhythm of celestial motions. The development of accurate timekeeping was crucial for navigation, particularly at sea, where determining longitude required knowing the precise time at a reference location. The problem of determining longitude was so important that the British government offered a substantial prize for its solution in the 18th century. The winner, John Harrison, created a series of marine chronometers that could keep accurate time even on the rolling deck of a ship, finally allowing navigators to determine their position anywhere on Earth's surface. But the quest for ever more accurate timekeeping revealed something unexpected. Earth's rotation is not perfectly constant. The length of a day varies slightly due to a variety of factors, from the gravitational influences of the moon and sun to changes in Earth's internal structure and even variations in atmospheric pressure and ocean currents. These tiny variations meant that astronomers needed to develop more sophisticated definitions of time that could account for the irregularities in Earth's rotation. The discovery that Earth's rotation was not perfectly regular was both surprising and profound. It meant that our planet, which had served as humanity's fundamental timekeeper for thousands of years, was not as perfect a clock as we had assumed. This realization led to the development of atomic clocks, which used the vibrations of atoms to measure time with incredible precision, and eventually to the redefinition of the second, based on atomic rather than astronomical phenomena. Yet even with atomic clocks that are accurate to billionths of a second, we still maintain the connection between human timekeeping and Earth's rotation. Our civil time is still based on the average length of a solar day, and we occasionally insert leap seconds into our timekeeping systems to keep our clocks synchronized with our planet's rotation. It's a beautiful example of how modern science both transcends and honors the ancient connection between time and celestial motion. The architecture of time also reveals itself in the biological rhythms that govern life on Earth. Virtually every living organism, from the simplest bacteria to the most complex mammals, has internal clocks that are synchronized with Earth's rotation. These circadian rhythms, from the Latin circa diem, meaning about a day, control everything from sleep-wake cycles to hormone production to cellular metabolism. The molecular mechanisms that drive these biological clocks are remarkably sophisticated, involving complex networks of genes and proteins that create self-sustaining oscillations with periods of approximately 24 hours. These molecular clocks are so fundamental to life that they exist in virtually every cell in our bodies, creating a hierarchy of biological timekeeping that extends from individual cells to entire organisms. Research in chronobiology has shown that these internal clocks are not just passive responders to the day-night cycle, but active participants in maintaining the temporal organization of life. When people are isolated from external time cues in underground bunkers or specially designed laboratory environments, their biological rhythms continue to oscillate with periods close to 24 hours, demonstrating that the rhythm of Earth's rotation has been literally encoded into the genetic machinery of life. The connection between biological time and Earth's rotation extends far beyond individual organisms to entire ecosystems. The timing of reproduction, migration, hibernation, and countless other biological processes is coordinated with the daily and seasonal cycles created by our planet's rotation and orbital motion. This temporal coordination is so important that disruptions to natural light cycles, such as those caused by artificial lighting in cities, can have significant effects on wildlife populations and ecological relationships. Human culture has also been profoundly shaped by the architecture of time created by Earth's rotation. The division of the day into hours, the structure of the work week, the rhythm of festivals and celebrations, all of these cultural patterns reflect humanity's deep connection to the cosmic cycles that govern our planet. Even in our modern world of electric lighting and global communications, we still organize our lives around the ancient rhythm of day and night, work and rest, activity and sleep. The study of how different cultures have understood and measured time reveals the universality of this connection to Earth's rotation. From the ancient Chinese water clocks to the Maya calendar systems, from the Islamic astronomical instruments to the mechanical clocks of medieval Europe, every human civilization has developed sophisticated methods for tracking and predicting the passage of time based on celestial motions. Modern physics has revealed that time itself is more complex and mysterious than our ancestors could have imagined. Einstein's theories of relativity show that time is not absolute but relative, flowing at different rates depending on gravity and motion. Time can slow down near massive objects or at high speeds, and space and time are intimately connected in a four-dimensional fabric called spacetime. Yet even these revolutionary insights don't diminish the importance of Earth's rotation in defining our human experience of time. While physicists may measure time with atomic clocks and define it in terms of quantum phenomena, our daily lives are still structured by the ancient rhythm of our spinning planet. The sunrise that marks the beginning of each day, the sunset that signals its end, the changing seasons that mark the passage of years, these natural timepieces remain as important today as they were to our earliest ancestors. As we look to the future, the architecture of time will continue to evolve. Proposals for missions to Mars must account for the different length of the Martian day, about 24 hours and 37 minutes, and the different seasonal cycles created by Mars's orbital period and axial tilt. Future space explorers will need to develop new temporal frameworks that account for the different rotational and orbital characteristics of other worlds. But for now, here on Earth, we remain connected to the cosmic timekeeper that has marked the passage of days and nights for billions of years. In the steady tick of our clocks, the rhythm of our heartbeats, and the cycle of our sleep and waking, we carry within us the memory of that ancient rotation, that fundamental spin that connects us to the forces that shaped our solar system and continues to influence every moment of our existence. Time's hidden architecture is built upon the foundation of Earth's rotation, creating the temporal framework within which all of human history and all of life itself has unfolded. There is something profoundly beautiful about recognizing that our Earth is not just a spinning ball of rock and metal, but a living, breathing, dynamic system where every component, from the deepest ocean trenches to the highest reaches of the atmosphere, is connected to every other component through an intricate web of interactions. The rotation of our planet is not separate from the life that flourishes on its surface, but rather an integral part of the complex system that makes life possible and, in turn, is influenced by the presence of that life. When we think about Earth's rotation, we often imagine it as a purely physical process, a massive sphere of rock spinning in space according to the laws of physics and astronomy. But the reality is far more complex and wonderful. The presence of life on Earth has fundamentally altered our planet's rotation in subtle but important ways, while the rotation itself has been one of the most important factors in shaping the evolution of life over billions of years. The atmosphere that surrounds our planet provides one of the clearest examples of how life and rotation interact. Earth's early atmosphere was very different from the oxygen-rich environment we know today. It was composed primarily of carbon dioxide, methane, and other gases that would be toxic to most modern life forms. The transformation of this atmosphere into one that could support complex life was largely the work of early photosynthetic organisms, first cyanobacteria and later plants, that converted carbon dioxide into oxygen over hundreds of millions of years. This atmospheric transformation had profound effects on Earth's rotation. The changing composition and density of the atmosphere altered the way it interacts with the solid Earth through friction and gravitational effects. The addition of large amounts of oxygen changed the chemical properties of the atmosphere in ways that affected everything from the formation of clouds to the absorption and reflection of solar radiation. These changes influenced weather patterns, which in turn affected the distribution of mass in the atmosphere and oceans, creating subtle but measurable effects on Earth's rotation. The daily breathing of our atmosphere, its expansion during the day as it's heated by the sun and contraction at night as it cools, creates atmospheric tides that are driven by Earth's rotation. These tides are much more subtle than ocean tides, but they're part of the complex feedback system that connects our planet's spin to its atmospheric dynamics. The rotation of Earth creates the Coriolis effect, which influences wind patterns and weather systems, while the movement of these atmospheric masses in turn exerts tiny but measurable effects on the planet's rotation. The oceans provide an even more dramatic example of how life and rotation interact. The vast bodies of water that cover more than 70% of Earth's surface are in constant motion, driven by a combination of solar heating, Earth's rotation, and the gravitational influences of the moon and sun. This motion creates the Great Ocean currents that help regulate our planet's climate by distributing heat from the tropics toward the poles and bringing cold water from polar regions toward the equator. But the oceans are not just passive bodies of water moving according to physical forces. They're teeming with life that actively participates in the circulation of water, nutrients, and heat around the planet. Marine organisms, from microscopic plankton to massive whales, affect ocean circulation through their movements, their metabolism, and their role in chemical cycles. The daily vertical migrations of countless marine organisms rising toward the surface at night and descending to deeper waters during the day create one of the largest movements of biomass on Earth. And this movement is synchronized with our planet's rotation, the ice caps and glaciers that exist at Earth's poles. And on high mountains represent another way that Earth's rotation interacts with its climate and life systems. The formation and melting of ice affects sea level, which in turn affects the distribution of mass on Earth's surface and can influence the planet's rotation. During ice ages, when vast amounts of water are locked up in continental ice sheets, the redistribution of mass from the oceans to the land actually speeds up Earth's rotation slightly, while the melting of ice has the opposite effect. But ice is not just a passive participant in Earth's climate system. It's also influenced by life in complex ways. The growth of forests and other vegetation affects local climate conditions, which can influence the formation and persistence of ice. Marine organisms affect ocean circulation patterns that determine where and how sea ice forms. Even the color of ice can be affected by living organisms. Algae and bacteria can darken ice surfaces, causing them to absorb more solar radiation and melt more quickly. The solid Earth itself is influenced by life in ways that connect to our planet's rotation. The weathering of rocks by lichens and other organisms affects the chemistry of soils and groundwater, which in turn affects the distribution of mass within the Earth's crust. The formation of limestone and other sedimentary rocks involves biological processes that move vast amounts of material from the oceans to the land, creating subtle changes in the distribution of mass that can influence Earth's rotation over geological timescales. Perhaps most remarkably, recent research has suggested that the evolution of complex life on Earth may have been directly influenced by changes in our planet's rotation. As Earth's rotation has slowed over geological time due to tidal friction, the length of days has gradually increased from perhaps 6 hours in the early Earth to our current 24-hour cycle. This changing day length may have influenced the evolution of photosynthesis, circadian rhythms, and other fundamental biological processes. Some scientists have proposed that the increase in day length may have been crucial for the evolution of complex multicellular life. Longer days would have allowed more time for photosynthesis, potentially increasing the amount of oxygen produced by early plants and algae. This increased oxygen production may have been necessary to create the oxygen-rich environment that complex animals require for their metabolism. The relationship between life and Earth's rotation also reveals itself in the fossil record. Ancient corals and other marine organisms show growth patterns that appear to be synchronized with daily and seasonal cycles. By studying these growth patterns in fossils, scientists can actually determine how fast Earth was rotating millions of years ago, and how the length of days has changed over geological time. These fossil timepieces show that about 400 million years ago, when the first forests were spreading across the land, a year contained about 400 days, each lasting about 22 hours. This means that the slowing of Earth's rotation can be tracked not just through astronomical calculations, but also through the biological records preserved in ancient life forms. Life itself has become a witness to the changing rhythm of our planet's spin. Modern life continues to be influenced by Earth's rotation in countless ways, many of which we're only beginning to understand. The migration patterns of birds and other animals are guided by magnetic fields and celestial cues that are ultimately connected to our planet's rotation and magnetic field. The timing of reproduction, hibernation, and other life cycle events is coordinated with the seasonal cycles created by Earth's tilted rotation axis. Even human activities are beginning to have measurable effects on Earth's rotation. The construction of large dams that impound vast amounts of water changes the distribution of mass on Earth's surface in ways that can be detected by precise measurements of our planet's rotation. The melting of ice due to climate change is redistributing mass from land to the oceans, creating subtle changes in Earth's moment of inertia and affecting the length of our days by tiny but measurable amounts. The study of how life and Earth's rotation interact has also revealed new perspectives on the search for life elsewhere in the universe. When astronomers look for potentially habitable planets around other stars, they consider not just whether the planet is at the right distance from its star to have liquid water, but also whether it has the right rotational characteristics to maintain a stable climate. Planets that rotate too slowly may have extreme temperature differences between their day and night sides, while planets that rotate too quickly may have chaotic weather patterns that make complex life difficult. The ideal conditions for life may require a delicate balance, a planet that rotates fast enough to distribute heat evenly around its surface, but slowly enough to allow complex biological processes to unfold. Earth's current 24-hour rotation period may represent something close to this optimal balance, refined over billions of years through the complex interactions between our planet's physical and biological systems. As we continue to study Earth as a living system, we're discovering new connections between rotation, climate, and life that reveal the profound unity underlying all natural processes on our planet. The spin that began when our world first formed from cosmic dust has become inextricably woven into the fabric of life itself, creating a planet where physical and biological processes are not separate phenomena, but parts of a single integrated system. In this perspective, Earth's rotation is not just the mechanical turning of a celestial body, but the heartbeat of a living world, the rhythm that has guided the evolution of life for billions of years and continues to shape every moment of our existence on this remarkable spinning planet we call home. There's perhaps no more beautiful or fundamental aspect of life on Earth than the gentle progression of seasons. The way spring emerges from winter with tender green shoots and warming days, the way summer arrives with its abundance of light and growth, the way autumn transforms the world with brilliant colors before winter returns with its quiet contemplation and rest. This seasonal cycle, which has shaped every aspect of life on our planet, exists because of a simple but profound fact. Earth's rotational axis is tilted at an angle of about 23.5 degrees relative to the plane of its orbit around the Sun. This tilt, which scientists call Earth's obliquity, is one of the most important legacies of the Great Collision between our planet and the Mars-sized body called Theia that occurred over 4 billion years ago. When Theia struck Earth in that ancient cosmic accident, it not only blasted material into space that would eventually form our moon, but also knocked our planet askew, giving it the tilted orientation that creates the seasonal rhythms we know today. To understand how this tilt creates seasons, imagine Earth as it travels around the Sun during the course of a year. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight and experiences longer days. This is summer in the north. 6 months later, when Earth has traveled to the opposite side of its orbit, the northern hemisphere is tilted away from the Sun, receiving less direct light and experiencing shorter days. This is winter in the north. Meanwhile, the southern hemisphere experiences the opposite pattern, with winter occurring when the north has summer, and vice versa. This elegant dance between Earth's tilted rotation and its orbital motion around the sun creates a pattern of seasonal change that has been remarkably stable for millions of years. The tilt angle of 23.5 degrees represents a kind of sweet spot, large enough to create distinct seasons that provide variety and change, but not so large as to create extreme temperature variations that would make complex life difficult to sustain. The seasonal cycle affects virtually every aspect of Earth's climate and weather systems. During summer in each hemisphere, the increased solar heating drives more vigorous weather patterns, stronger winds, and more active storm systems. The longer days and more intense sunlight fuel increased evaporation from oceans and lakes, creating more clouds and precipitation. Plants respond to the increased light and warmth by accelerating their growth, producing the green abundance that characterizes summer landscapes. Winter brings a different kind of beauty and activity. The reduced solar heating allows different atmospheric circulation patterns to develop, often bringing cold air masses from polar regions toward lower latitudes. The shorter days and weaker sunlight slow plant growth and cause many species to enter dormancy. Snow and ice form in regions where temperatures drop below freezing, creating brilliant white landscapes that reflect sunlight back to space and help to cool the planet. The transition seasons, spring and autumn, are perhaps the most dynamic of all, as Earth's climate systems adjust to the changing patterns of solar heating. Spring brings the warming that melts winter ice and snow, sending water flowing into rivers and streams, recharging groundwater systems, and awakening dormant plant life. Autumn brings the cooling that triggers spectacular color changes in deciduous forests as trees prepare for winter dormancy, and often creates some of the most stable and pleasant weather conditions of the year. These seasonal patterns have shaped the evolution of life on Earth in profound ways. The regular cycle of abundance and scarcity, growth and dormancy, has led to the development of complex life strategies that take advantage of seasonal opportunities while surviving seasonal challenges. Migration patterns, breeding cycles, hibernation, seed production, and countless other biological phenomena are timed to coordinate with the seasonal rhythms created by Earth's tilted rotation. Birds that migrate thousands of miles between summer and winter habitats are following paths that have been refined over millions of years to take advantage of seasonal changes in food availability, weather patterns, and daylight hours. The timing of their migrations is so precisely coordinated with seasonal changes that many species can predict optimal departure and arrival times with remarkable accuracy, using internal biological clocks that are ultimately synchronized with Earth's rotational and orbital cycles. Plants have evolved equally sophisticated responses to seasonal changes. Deciduous trees that shed their leaves in autumn are responding to the decreasing daylight hours that signal the approach of winter. This response is triggered by specialized photoreceptor molecules that can detect subtle changes in the length of day and night, allowing trees to begin their preparations for winter dormancy at exactly the right time. Many flowering plants have evolved to coordinate their reproductive cycles with specific seasons, ensuring that flowers bloom when pollinators are most active and that seeds mature when conditions are optimal for dispersal and germination. Some plants, like cherry trees and tulips, require a period of cold winter temperatures before they can bloom in spring. a process called vernalization that ensures they don't waste energy blooming at the wrong time of year. The seasonal cycle also drives some of the most important chemical and physical processes on Earth. The formation and melting of sea ice in polar regions follows a seasonal pattern that affects ocean circulation, marine ecosystems, and global climate patterns. The seasonal growth and dormancy of vegetation affects the concentration of carbon dioxide in the atmosphere, creating annual cycles that can be measured at monitoring stations around the world. In the Northern Hemisphere, atmospheric carbon dioxide levels are lowest during summer, when vigorous plant growth removes CO2 from the air through photosynthesis. Levels are highest during winter, when plant growth slows and decomposition of organic matter releases stored carbon back to the atmosphere. This seasonal breathing of the biosphere creates annual fluctuations in atmospheric composition that demonstrate the intimate connection between Earth's rotation, its climate, and its living systems. Human civilizations have been shaped by seasonal cycles in ways that extend far beyond agriculture and food production. The development of art, music, literature, and religious traditions has been profoundly influenced by the rhythm of seasons. Seasonal festivals and celebrations exist in virtually every human culture, often timed to coincide with solstices, equinoxes, and other astronomical events that mark the progression of Earth's tilted journey around the sun. The winter solstice, the day when the sun reaches its lowest point in the sky and daylight hours are shortest, has been celebrated by human cultures throughout history as a time of renewal and hope, marking the moment when days begin to lengthen again. The summer solstice, when daylight hours are longest, has traditionally been a time of celebration and abundance, recognizing the peak of the solar year. The spring and autumn equinoxes, when day and night are equal in length everywhere on Earth, have been seen as times of balance and transition, moments when the seasonal cycle pauses in perfect equilibrium before continuing its eternal progression. These astronomical events, which are direct consequences of Earth's tilted rotation, have provided humanity with some of its most profound symbols and metaphors for the cycles of life, death, and renewal. Modern science has revealed that Earth's axial tilt is not perfectly constant, but varies slowly over timescales of thousands of years. These variations, combined with changes in the shape of Earth's orbit and the timing of its closest approach to the Sun, create complex cycles that influence long-term climate patterns. These Milankovitch cycles, named after the Serbian astronomer who first described them mathematically, help explain the ice ages and other major climate changes that have occurred throughout Earth's history. Currently, Earth's tilt varies between about 22.1 and 24.5 degrees over a cycle of approximately 41,000 years. We're currently near the middle of this range, with our 23.5-degree tilt providing the moderate seasonal contrasts that characterize our current climate. When the tilt is at its minimum, seasonal contrasts are reduced, potentially leading to cooler summers that allow ice sheets to persist and grow. When the tilt is at its maximum, seasonal contrasts are enhanced, with hotter summers and colder winters. These long-term variations in Earth's tilt demonstrate that even the seasonal patterns we think of as permanent and unchanging are actually part of much larger cycles that unfold over geological time. The seasons that have shaped human civilization and influenced the evolution of life are themselves slowly evolving, part of the continuing story of Earth's dynamic relationship with the cosmos. As we face the challenges of climate change in the modern world, understanding the role of seasonal cycles becomes increasingly important. Changes in temperature and precipitation patterns are already affecting the timing of seasonal events. Spring is arriving earlier in many regions. Autumn is lasting longer, and the boundaries between seasons are becoming less distinct. These changes have profound implications for agriculture, wildlife populations, and human societies that have evolved to depend on predictable seasonal rhythms. Yet through all these changes, the fundamental cause of seasons, Earth's tilted rotation as it orbits the Sun, remains constant on human timescales. The 23.5-degree tilt that creates our seasonal world will continue to drive the cycle of summer and winter, growth and dormancy, abundance and scarcity for thousands of generations to come. In this constancy, we find both comfort and responsibility. Comfort in knowing that the seasonal rhythms that have shaped life on Earth will continue, and responsibility to ensure that we don't disrupt these ancient patterns in ways that harm the delicate balance of natural systems that depend on them. The seasons created by Earth's tilted rotation represent one of the most beautiful examples of how a simple astronomical fact, the angle at which our planet spins, can create patterns of beauty and complexity that influence every aspect of life on Earth, from the microscopic timing of cellular processes to the grand migrations of animals across continents, from the annual cycles of human agriculture to the long-term patterns of climate change. The seasons touch every part of our world with their gentle but persistent influence. In the progression from spring to summer to autumn to winter and back to spring again, we see reflected the larger story of Earth's relationship with the cosmos, a story of cycles within cycles, of stability within change, of the profound connections that link the spinning of our planet to the rhythms of life itself. When we step back and consider Earth's rotation from the vast perspective of the cosmos, we begin to see our spinning planet not as an isolated world, but as part of an intricate cosmic symphony where galaxies, stars, and planets all participate in the grand dance of the universe. This cosmic perspective reveals that the rotation of our Earth is connected to processes and forces that operate on scales almost too large to comprehend. From the formation of our local galaxy to the expansion of the universe itself, our solar system exists within the Milky Way galaxy, a vast collection of hundreds of billions of stars arranged in a beautiful spiral pattern that spans about 100,000 light years from edge to edge. The entire galaxy is rotating, turning majestically on its axis with a period of about 225 million years, what astronomers sometimes call a galactic year. Our solar system, located about 26,000 light years from the galactic center, participates in this rotation, carrying Earth and all the other planets on a vast circular journey through interstellar space. This galactic rotation has subtle but real effects on our solar system and Earth's rotation. As we orbit the galactic center, we pass through regions of space with different densities of stars, gas, and dust. These variations can influence the gravitational environment of our solar system in ways that may affect the long-term stability of planetary orbits and rotations. We also pass through the spiral arms of our galaxy periodically, encountering increased stellar formation activity and potentially higher levels of cosmic radiation. The relationship between Earth's rotation and galactic rotation demonstrates one of the most beautiful aspects of cosmic organization, the way that rotational motions exist at every scale, from subatomic particles to entire galaxies, and how these rotations at different scales can influence each other. Earth spins on its axis once per day, orbits the Sun once per year, and participates in the galaxy's rotation once every 225 million years. Each of these rotational periods represents a different aspect of our cosmic address and influences our planet in different ways. When we look even further out into the universe, we discover that our galaxy itself is part of a larger structure called the local group, which includes the nearby Andromeda galaxy and several dozen smaller galaxies. The local group is gravitationally bound together and appears to be slowly rotating as a whole, though over time scales so vast that the motion is barely detectable. This represents yet another level of cosmic rotation that influences the environment in which our galaxy, our solar system, and our Earth exist. The cosmic perspective also reveals how Earth's rotation connects to the fundamental forces and processes that govern the universe. The conservation of angular momentum that caused our planet to spin as it formed from the solar nebula is the same principle that governs the rotation of galaxies, the spin of neutron stars, and even the quantum mechanical properties of elementary particles. In this sense, Earth's daily rotation is a local manifestation of one of the most fundamental principles in physics. The magnetic field generated by Earth's rotation connects our planet to the broader electromagnetic environment of our solar system and galaxy. The solar wind, that constant stream of charged particles flowing from the sun, carries with it magnetic field lines that interact with Earth's magnetic field, creating complex patterns of electromagnetic activity that extend far into space. These interactions connect Earth to the magnetic environment of the entire solar system. Our galaxy also has its own magnetic field, generated by the complex motions of ionized gas and plasma throughout the galactic disk. This galactic magnetic field influences the propagation of cosmic rays, high-energy particles that travel through interstellar space, and may have subtle effects on the magnetic environment of our solar system. The relationship between Earth's magnetic field and the galactic magnetic field represents another connection between our planet's rotation and the cosmic environment in which we exist. The search for exoplanets, planets orbiting other stars, has revealed that planetary rotation is a common phenomenon throughout the universe, but with an amazing variety of characteristics. Some planets are tidally locked to their stars, with one side permanently facing the star and the other side permanently dark. Others rotate extremely rapidly, with day lengths measured in hours rather than Earth's 24-hour period. Still others have been knocked askew by cosmic collisions, creating extreme axial tilts that produce bizarre seasonal patterns. This diversity of planetary rotations throughout the galaxy helps us appreciate how special Earth's rotation really is. Our 24-hour day length, our moderate axial tilt, our stable rotational axis, all of these characteristics represent a fortunate combination that has helped make Earth suitable for complex life. When astronomers search for potentially habitable worlds around other stars, they consider rotational characteristics as one of the important factors that determine whether a planet might be able to support life as we know it. The cosmic perspective also reveals the ultimate fate of Earth's rotation over unimaginably vast time scales. As our sun evolves and eventually becomes a red giant star in about 5 billion years, the changing gravitational environment may affect Earth's rotation. The sun's outer atmosphere may expand to engulf our planet entirely, but even if Earth survives, its rotation will certainly be influenced by the dramatically different conditions in the solar system. On even longer timescales, the expansion of the universe itself may eventually affect the rotation of planets and stars. Current cosmological models suggest that the universe will continue expanding and cooling for trillions of years, eventually becoming a cold, dark place where stars no longer form and existing stars gradually burn out. In such a distant future, the rotation of planets like Earth will be among the last remnants of the cosmic processes that once filled the universe with light and motion. But the cosmic perspective also reveals something profound about the nature of time and existence. The rotation of Earth that marks our days and years is part of a vast hierarchy of cosmic rhythms, from the quantum fluctuations that occur in fractions of seconds to the evolution of galaxies over billions of years. Each level of this hierarchy influences the others, creating a universe where local phenomena like Earth's rotation are connected to the largest scale structures and processes in the cosmos. The study of Earth's rotation from a cosmic perspective has also contributed to our understanding of fundamental physics. Precise measurements of our planet's rotation have been used to test Einstein's theory of general relativity, to search for evidence of gravitational waves, and to explore the properties of space and time themselves. In this sense, Earth serves as a cosmic laboratory where the rotation of our planet helps us understand the basic laws that govern the universe. The cosmic perspective reminds us that Earth's rotation is not just a local phenomenon that affects weather patterns and biological rhythms on our planet, but part of a vast, interconnected system that extends from the quantum level to the scale of the observable universe. The same forces that set our planet spinning billions of years ago continue to operate throughout the cosmos, creating new stars, new planets, and potentially new worlds where rotation will once again play a crucial role in determining the conditions for life. When we contemplate Earth's rotation from this cosmic viewpoint, we gain a deeper appreciation for both the specialness of our planet and its profound connection to the universe as a whole. We are not isolated inhabitants of a lonely world, but participants in a cosmic story that began with the Big Bang and continues to unfold around us every day. The rotation that brings us each new sunrise and sunset connects us to processes that operate on scales from the subatomic to the cosmic, reminding us that we are truly citizens of the universe, spinning through space on a planet that carries within its rotation the memory of cosmic forces and the promise of cosmic futures yet to come. In this cosmic perspective, the secret language of the universe reveals itself not as an abstract mathematical concept, but as a living reality that speaks through every aspect of our world's rotation. From the quantum spins of particles in Earth's core to the vast rotation of our galaxy, the universe communicates through patterns of motion, cycles of time, and the elegant mathematics that describes how everything moves in relation to everything else. Earth's rotation is one voice in this cosmic chorus, a unique and beautiful expression of the fundamental principles that organize and animate the entire universe. Through understanding our planet's spin, we begin to hear the larger symphony of which we are all a part, and to appreciate our place in the grand cosmic dance that connects every atom, every planet, every star, and every galaxy in one magnificent, rotating, ever-changing whole. As we stand at this moment in Earth's long history, looking both backward toward the ancient forces that set our world spinning and forward toward the unimaginable futures that await, we find ourselves part of a story that is still being written. The rotation of our planet, which began in the cosmic violence of solar system formation over 4 billion years ago, continues to evolve and change, responding to forces both terrestrial and cosmic that will shape the destiny of our spinning world for billions of years to come. The most immediate and measurable change in Earth's rotation is the gradual slowing caused by tidal friction from the Moon. This process, which has been operating for billions of years, continues today at a rate that lengthens each day by about 1.7 milliseconds per century. While this might seem insignificantly small, over geological timescales, it adds up to dramatic changes. If we could travel forward in time by several 100 million years, we would find an Earth where days last significantly longer than our current 24 hours. But the Moon's influence on Earth's rotation will not continue unchanged forever. Our satellite is gradually moving away from Earth at a rate of about 3.8 centimeters per year, and as it becomes more distant, its gravitational influence on our planet's rotation will weaken. Eventually, billions of years from now, Earth and the Moon may become tidally locked to each other, with the same side of Earth always facing the Moon, just as the same side of the Moon currently always faces Earth. If this tidal locking occurs, it would represent one of the most dramatic changes in Earth's rotation since the Great Collision that created the Moon in the first place. Days on Earth would last much longer, potentially weeks or even months, with one hemisphere experiencing extended periods of sunlight while the other remains in darkness. Such extreme day-night cycles would create radically different climate patterns and would likely make much of Earth's surface unsuitable for life as we know it. However, this tidal locking scenario assumes that the Sun will remain stable and that no other major perturbations affect the Earth-Moon system. In reality, our Sun is slowly but steadily growing brighter as it ages, increasing its energy output by about 10% every billion years. This brightening will gradually heat Earth's atmosphere and oceans, potentially triggering a runaway greenhouse effect that could boil away our oceans within the next billion years or so. Even before that extreme scenario unfolds, the changing solar output will affect Earth's climate in ways that could influence our planet's rotation. Changes in the distribution of ice, water, and atmospheric mass due to climate change will alter Earth's moment of inertia, its resistance to rotational changes, creating subtle but measurable effects on the length of our days and the orientation of our rotational axis. We're already seeing some of these effects in the modern era due to human-induced climate change. The melting of glaciers and ice sheets is redistributing mass from land to the oceans, while changes in atmospheric circulation patterns are altering the distribution of air mass around the planet. These changes are creating measurable variations in Earth's rotation that can be detected by precise astronomical observations and satellite measurements. The continued melting of ice due to global warming could have increasingly significant effects on Earth's rotation in the coming centuries. If the Greenland and Antarctic ice sheets were to melt completely, the redistribution of that water to the oceans would measurably slow Earth's rotation, making days slightly longer. The changing distribution of mass would also affect the orientation of Earth's rotational axis, potentially shifting the locations of the north and south poles by small but detectable amounts. Human activities beyond climate change may also influence Earth's rotation in subtle ways. The construction of massive infrastructure projects like large dams and reservoirs changes the distribution of mass on Earth's surface in ways that can be measured by sensitive instruments. As human civilization continues to grow and modify Earth's surface, these effects may become more significant, representing the first time in Earth's history that the actions of living organisms have had measurable effects on planetary rotation. Looking further into the future, the evolution of our sun will eventually have dramatic effects on the entire solar system, including Earth's rotation. In about 5 billion years, the sun will begin to exhaust the hydrogen fuel in its core and start to expand into a red giant star. This expansion will dramatically change the gravitational environment of the inner solar system and may significantly affect Earth's orbit and rotation. Some models suggest that Earth's orbit will expand as the sun loses mass during its red giant phase, potentially saving our planet from being engulfed by the sun's expanding outer atmosphere. If Earth survives this transition, it will find itself orbiting a much larger but cooler star, with dramatically different conditions that would certainly affect its rotation. The reduced solar heating might even allow some of Earth's atmosphere and oceans to persist, though in forms very different from what we know today. Eventually, the sun will shed its outer layers and become a white dwarf star, a small, dense remnant about the size of Earth, but with a mass comparable to our current sun. If Earth survives to the stage, it would find itself orbiting a white dwarf in a cold, dark solar system where the only warmth comes from the gradual cooling of the stellar remnant. Earth's rotation would continue, but the planet would be frozen and lifeless, spinning through a cosmos very different from the one in which it was born. On even longer timescales, the future of Earth's rotation becomes connected to the ultimate fate of the universe itself. Current cosmological models suggest that the universe will continue expanding and cooling for trillions of years, eventually becoming a cold, dark place where stars no longer form and existing structures gradually decay through various quantum processes. In such a distant future, Earth's rotation might be one of the last vestiges of the cosmic processes that once filled the universe with motion and energy. Planets orbiting white dwarf stars could continue spinning for trillions of years, gradually slowing due to various subtle effects but maintaining their rotation long after all other large-scale motions in the universe have ceased. But perhaps the most fascinating aspect of Earth's rotational future lies not in these distant scenarios, but in the potential for life, including human civilization, to actively influence and even control our planet's rotation. As our understanding of planetary mechanics continues to advance, we might develop technologies that could deliberately modify Earth's rotation for various purposes. For example, if climate change or other factors made it desirable to alter the length of Earth's days, future civilizations might be able to use large-scale engineering projects to speed up or slow down our planet's rotation. Moving large amounts of mass toward or away from Earth's rotational axis could change the planet's moment of inertia, similar to the way a figure skater controls their spin by moving their arms. Such planetary engineering would require technologies far beyond our current capabilities, but it's not beyond the realm of physical possibility. If human civilization continues to advance for thousands or millions of years, deliberately controlling Earth's rotation might become as routine as controlling the flow of rivers or the composition of the atmosphere. The search for life on other planets and the eventual prospect of human expansion to other worlds will also provide new perspectives on planetary rotation. As we establish colonies on Mars with its 24.6-hour day, or on other worlds with different rotational characteristics, we'll learn how different day lengths affect human biology and society. This knowledge might inform decisions about whether and how to modify the rotation of worlds we colonize or even terraform. The study of exoplanets continues to reveal the incredible diversity of planetary rotations throughout the galaxy, from tidally locked worlds with permanent day and night sides to rapidly spinning planets with days lasting only a few hours. As our ability to study these distant worlds improves, we'll gain new insights into how planetary rotation affects the potential for life and the evolution of planetary systems. Perhaps most remarkably, the future study of Earth's rotation may help us understand some of the deepest questions in physics and cosmology. Precise measurements of our planet's rotation are already being used to test theories of gravity, search for evidence of dark matter, and explore the fundamental properties of space and time. As our measurement capabilities continue to improve, Earth's rotation may serve as a laboratory for discovering new physics and understanding the ultimate nature of reality. Through all of these possible futures, near and far, dramatic and subtle, the fundamental beauty of Earth's rotation remains constant. The same principles of angular momentum conservation that set our world spinning billions of years ago will continue to govern its motion, whether it's spinning in the warm light of our current sun, the dim glow of a white dwarf, or the cold darkness of a universe where stars no longer shine. In contemplating the future of our spinning world, we're reminded that we are temporary passengers on a planet whose rotation connects it to cosmic forces and timescales that dwarf human experience. Yet we are also reminded of our unique position as the first known life forms on Earth, capable of understanding that rotation, predicting its future changes, and perhaps even influencing its evolution. We are both observers and participants in the story of Earth's rotation, witnesses to its ancient past and potential architects of its future. In this role, we carry a responsibility to understand and preserve the delicate balance of forces that has made our spinning world a haven for life, while also embracing the possibility that we might someday help guide that rotation toward futures we can only begin to imagine. Thank you for staying with me through this peaceful journey into what the futures we can only begin to imagine. Thank you for staying with me through this peaceful journey into rotation, the peaceful journey into when the Earth started spinning, the secret language of the universe. I hope that as you go about your daily life, you'll carry with you a deeper appreciation for the incredible cosmic dance that brings us each new sunrise and sunset. The rotation of our planet, which began in the violence of stellar birth and planetary collision, has become the gentle rhythm that marks our days and connects us to the vast universe around us. Remember that every time you watch the sun rise or set, every time you notice the stars wheeling overhead, every time you feel the changing of the seasons, you're witnessing the continuing story of that ancient spin that set our world in motion billions of years ago. The secret language of the universe speaks through these daily miracles, reminding us that we are part of something far larger and more beautiful than we often realize. If you found peace and wonder in this journey through cosmic time, I'd be grateful if you'd share it with others who might also enjoy exploring the gentle mysteries of our universe. Until we meet again, may your days be filled with the quiet joy that comes from knowing your place in the cosmic dance. And may you always find comfort in the steady, reliable spin of our beautiful home planet. Sweet dreams, and thank you for joining me in celebrating the magnificent story of when the Earth started spinning, the secret language of the universe.